Let me talk a little bit about the structure of amines. They have a carbon-nitrogen bond. Nitrogen needs to have two other things bonded to it, so those could be hydrogens or alkyl groups. And when I say alkyl, aryl would be fine too. Could be a phenyl ring. Nitrogen only has three things bonded to it because it has a lone pair of electrons filling that valence shell. So it has 8 electrons in the valence shell. And this carbon is not a carbonyl group. If it were, the compound would be an amide, not an amine. So I'm going to put three things bonded to carbon. I've indicated that these could be hydrogens or alkyl groups bonded to the nitrogen, so there really are three categories of amines, aren't there? There are amines that have one alkyl group and two hydrogens. We call those primary amines. Others have two alkyl groups and one hydrogen. We call those secondary amines. And the amines that have three alkyl groups attached to nitrogen are tertiary amines. Notice that this is very different from how we use primary, secondary, and tertiary when we name alcohols. When we're talking about alcohols, we're talking about the carbon that the OH is attached to. But in this case, we're talking about the number of carbons that are attached directly to the nitrogen. This nitrogen has 4 pairs of electrons around it, so we would say it should be sp3 hybridized. It is. And we would say that makes it tetrahedral. I'm going to get back to that tetrahedral business in just a minute. Let's draw the structure first. I'm going to draw that lone pair of electrons in an sp3 orbital here. And that puts the orientation of the three things that are attached to nitrogen. Something like this. They're all sticking down. One sticks straight toward us and the others stick back. Now this is indeed a tetrahedral arrangement of the orbitals around nitrogen. But would we call this a tetrahedral arrangement of the molecule? Not really, would we? Because when we look at the atoms, we see the nitrogen and the three things attached to it. That electron pair doesn't show up. So amines, in a way, are really trigonopyramidal. And we would say if there are three different things attached to this nitrogen, the fourth is a pair of electrons, we have 4 different things arranged around that nitrogen, and it should be chiral. So I'm going to put R1, R2, and R3, and say that this is chiral. But in normal amines, when we look, they don't appear to be chiral. That's because the 2 enantiomers are in equilibrium. There's rapid inversion, so that at any one moment we have both enantiomers present in equal amounts. Amines are not chiral at nitrogen unless there's something that prevents this inversion. For example, if all 3 of these R groups were tied together, then the inversion couldn't take place, and in those cases, chirality at nitrogen is observed. Okay, so we have tetrahedral nitrogen. We have trigonopyramidal for the geometry of the molecule itself. The orbitals are arranged in a tetrahedral manner. There's another group of compounds I want to talk about. The compounds are called Hetero Cycles, and they have a nitrogen inner ring. Pyrrolidine is an example. 5-membered ring with nitrogen as part of the ring in place of a carbon. Pyrrole is another example. This is actually an aromatic heterocycle, and you've seen a third one that's a 5-membered ring, imidazole. It too is aromatic. 6-membered rings are common. In fact, you've even seen one, pyridine. And the saturated analog of pyridine is piperidine. These 5 heterocycles are real common, along with quite a few others. All of the amines for the nucleic acid bases, for instance, are heterocycles. There's an enormous amount of chemistry about heterocycles, a field all to itself. It even has its own journal, the Journal of Heterocyclic Chemistry. And the chemistry is really pretty special and biologically extremely important. Because it's such a special field, I won't talk much about heterocyclic chemistry. There's another group of compounds that's really closely related to amines. They're called ammonium salts. You've seen something like it in general chemistry when you saw ammonium chloride. Nitrogen can be bonded to 4 things, not 3. When it is, it doesn't have a lone pair of electrons, but rather has used that lone pair to make a bond to something else. So it has a positive charge. There will always be some kind of an anion associated with it. These are called ammonium salts, and they turn out to be pretty important in medicinal uses. Here's a rather fun example. The compound is called diphenhydramine, and pH stands for phenyl. I'll write Me for methyl. This is the active antihistamine constituent in Benadryl. But here's the fun part. It's also the active constituent in Sominex and Z-Quil. Those names sound a whole lot like their sleep aids, don't they? And in fact, they are. This compound is a hypnotic. It helps put people to sleep. So if you're using Benadryl as an antihistamine, you shouldn't be real surprised if you feel pretty darn drowsy. It's marketed both as an antihistamine and a sleep aid in exactly the same doses. Now, if you check me by looking at the packaging of Benadryl, Z-Quil, Sominex, you won't see diphenhydramine alone as the active constituent, but rather it will have a different name. It will be called diphenhydramine hydrochloride. This is one way to name ammonium salts, and actually the compound in the package itself is an ammonium salt. So I need to add a hydrogen here. The nitrogen will have a positive charge, and because it's called hydrochloride, we know that the anion is chloride. And so why is it diphenhydramine hydrochloride when the active constituent itself is diphenhydramine? Well, there are important reasons. In addition to being much easier to handle, ammonium salts are far more soluble in water. That's important for medicines that we want to ingest. And it's much more stable. So it has much better shelf life. So these ammonium salts are easier to handle, water soluble, and have greater stability. What's not to like? So when you look at the packaging of a whole lot of pharmaceutical agents that you can buy in the store, you'll see that many of them call themselves hydrochlorides or hydrobromide, or have an ammonium type of name, which means that they're ammonium salts. And finally, let me say just a little bit about the chemistry of amines. What I want to do is show you that the chemistry of amines is easily predicted on the basis of things you know already, so it'll be easy to understand. The key to understanding nitrogen chemistry is to focus on this unshared electron pair. Recall that nitrogen is much less electronegative than oxygen, so that electron pair is not held as tightly. That pair is more readily shared to form a new bond. Now that bond could be to a proton, which means amines act as bases, or that bond could be formed to a carbon, which means amines act as nucleophiles. So without thinking any more than this, we can list the two most important types of reactivity of amines. There is a third one that's very important that we won't talk about except for me to mention it right now. And that is amines are easily oxidized. And this is a bad thing. Remember I said ammonium salts increase the shelf life of pharmaceuticals? Well, this is the reason. The ammonium salts are not easily oxidized, but the amines are. So the oxidation is something we don't want to happen. The other two things are things that we can exploit in chemistry, and we do all the time, both in organic synthesis and Mother Nature exploits it too. Amines are important bases and nucleophiles in biological chemistry.